right, guys. So before I move on, we spoke about limits at infinity. Would anybody here like to tell me what do I do to the function when I push x to infinity, to the sideways 8 symbol? What am I actually doing to the function? What do you mean nothing? When I push x towards infinity, what do I actually do to the function? You're plugging a very large number. Yes, David, a very large number. Good. Very close. If I push towards the number a, what is to infinity? It means a very large number. It might not. Now the question is, what is a horizontal asymptote, guys? All right, guys, welcome all of you. And again, most of you are turning your cameras off. That's a beginning of a bad trend. So again, if you are not in a situation where you're compromised, please turn your cameras on so I can see what you're doing and if you're able to understand me. Exactly, Humira. The function begins to look similar to something familiar. That's what an asymptote is. An asymptote is just let's call it a vague word for something familiar. Now, what is a horizontal asymptote specifically? What object is that thing? Horizontal asymptote is what? A y value of the graph, but more specifically, what is a horizontal asymptote? Infinity, very vague. What is a horizontal asymptote? What shape am I going to see? All right, so you see, guys, visual is extremely important here. A curved line, well, a curve in a line is different, right? So a curve, let's look at this, guys. I haven't taught you trigonometry yet, so you can be okay, but this is the graph of cosine of 1 over x. Now, when I ask what's limit as x goes to infinity, what do I do to the picture of the graph? Where am I looking? I drag the graph to the right. Do you see? Look what happens. I drag the graph to the right. You see what's happening? The shape that I'm looking at is on the right. And you can see that the curve is meandering, crossing the x-axis many times. In fact, it will cross the x-axis infinitely many times. But look what happens as I move further and further and further and further and further and further to the right. Do you see what's happening, guys? Do you see what's happening? Are you with me? Tell me what's happening, please. What are you seeing? What are you seeing? It becomes a line. In particular, what sort of line? A horizontal line. Do you understand when you say horizontal? Because it's visual. Yeah? If you're in a train, you're driving along this plane further and further to the right. What are you seeing? You are seeing a plane. Since it's one-dimensional, it's going to be linear. Do you understand? It's going to be a horizontal line, and the graph of horizontal line is y equals 1. You don't have to know that in here. This line will be getting closer and closer to 1. You see, I mean, here it's still below 1, but it will kind of gradually be climbing towards 1 because the limit is 1. We will see how I know it later on. Do you understand? So without seeing the shape of the graph, if I scrolled very far to the right, it's indistinguishable from a line. Now, if you think an asymptote is something that cannot be crossed or some vague definitions, that's nonsense, okay? An asymptote is very simply the familiar shape that you're comparing the graph to. Do you see? You cannot distinguish this curve from a line y equals 1 eventually. As you move far enough to the right, it looks to you like a horizontal line. You understand? That's what when you're asking, does the function have asymptotes, you're just asking, does the function become something familiar? And if you ask horizontal asymptote, specifically, you're asking for a horizontal line. Do you understand why the graph y equals 1 is the way you specify this line? Because no matter what x is, look at it, I change my x's, you see? This floating point is the altitude. No matter what's my x, it's essentially the same height. The y is the same height. That's why I say y equals 1 is the horizontal asymptote. Are we clear? Now, do you all know what is an EKG? Yes? You do? Could you tell me what is the, does your EKG, if you could record it for the rest of your life, does it have an asymptote? And what asymptote would that be? Flat line, precisely, Robert. Right? If you move through the graph of your EKG, you will see that you have a horizontal asymptote, which if you normalize it, maybe it's 0. That means you have no heartbeat. Good? That's why I was so annoyed last time. I mean, you see, I have this measuring thing, and it measures that I have no heartbeat whatsoever. Of course, that's to be expected, since I died in '83. And I was trying to find my shadow, but so far, no luck. Good? Okay, wonderful. So the thing is, we don't always have the assistance of the computer. We don't have the assistance of the computer. And what we do is we figure out the asymptote by means of calculation. You understand? We allow mathematics to be our eyesight. We replace our eyes with very powerful ones, with mathematical eyes. So tell me, please, what do I do here? So look at it. I want to find the horizontal asymptotes for the function f of x equal to 2x cubed plus x minus 1 over x cubed plus x squared plus 5. What do I actually do to figure out the asymptote? Now look what I do. If I want to scroll the graph to the right, I can try to find several horizontal asymptotes if they exist. I can move my graph to the right, or I can move my graph to the left. You understand? I can go either left or right. Now, if I decide to go right, I push limit as x goes to infinity. That's only meaning that your x coordinate is going to be larger and larger. That means you're walking to the right. Clear? So what I do to find this limit, I factor out x cubed from the numerator. That's the biggest power. X cubed factor out. And on the denominator, I do the same thing. I factor x cubed. Why do I do that? Because then I can cross them out. They are positive numbers. X is just a large number. So this crosses out. And I'm left with limit as x goes to infinity of 2 plus 1 over x squared minus 1 over x cubed divided by 1 plus 1 over x plus 5 over x cubed. You with me? So you see, I can factor it. Even though you don't see an x cubed here, you obviously can factor. The limit of what, Francis? The question is the limit of what? If you are searching for horizontal asymptotes, right? How can a line be horizontal? It's like if you are walking parallel to the curve, the graph looks like a horizontal line. Good? That's all it is. So we look at it, and when we take the limit, do you all see that the limit is 2? So if the limit is 2, what is it talking about? The limit 2 means that as I change my x coordinate to the y coordinate described by this function. You see, the graph and the function are not the same. The function is only the y coordinate of my graph. I have x, and then there's a y coordinate. The altitude is calculation based on where you're standing. So the calculation is essentially just 2. You see, it's not truly 2, but if x is very large, the calculation amounts to just pretty much putting 2 for the altitude. That means that we have a horizontal asymptote if we move to the right. Do you understand? Now, please tell me what happens if I move to the left. Will I have a horizontal asymptote there or not? Let's now move all the way to the left. Help me do that. Calculate. Now calculate it. If you say there's going to be a horizontal asymptote, tell me what that will be. Quickly. Yes, when x goes to negative infinity, what will be my horizontal asymptote, or do I not have it? Exactly, Christina. Calculation is exactly the same. It ends up being 2 as well. So if I move to the left, it will be 2. You see, I take limit to x going to minus infinity. Good? Yes, Giovanni. Factoring of the highest term is just because they are going to, I want everything to be divided by the highest term that will crush everything to 0. You see, I factor out x cubed. Do you see that x cubed times 2 is 2x cubed? Now what do I need here? I need to take x divided by x cubed. Do you see that? Because if I multiply the x cubed by this fraction, I will get x again. And here I need 1 over x cubed. Just divide all the other terms by x cubed. When you factor out, just write the term out and divide everything, because you see, guys, that's another problem. You are not familiar with basic arithmetic. So this, through parentheses, we have the distributive law. So this number goes here, 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 right? So then what you do is reverse that. Good? So you just pretty much write the x cube out, and then in parentheses, you write everything, every term divided by what you factored out. That's as much as you do. Now, obviously, there's horizontal asymptotes of this form. 1 over x, if you push x to plus or minus infinity, it will be 0, which means y equals 0 is your horizontal asymptote for functions of the form 1 over x. Okay? Now, again, there is nothing at all special to horizontal asymptote. You see, you can have an equation of the line mx plus b, and that will be called, in general, an oblique asymptote. You understand? If you scroll to the right or to the left and you see a straight line but not a horizontal one, you can still say that, why not? That's an asymptote, right? It looks like, in other words, when you say I have an asymptote, you're saying I'm observing some familiar shape. That's all you're saying, okay? And what is that familiar shape? It could be a horizontal line, or it could be a slanted line. Good? Or even if you want to, you can stretch that idea further. You can say I have a quadratic asymptote. In other words, I look to the right and it looks to me like I'm observing a quadratic. It looks like a parabola of sorts, right? Or it looks like a cubic. It doesn't matter. It's just comparison to a shape that you deem familiar. Okay? So let's look at this example. Find the asymptotes, guys. Can you see this? 1 plus x to the 6 divided by 1 plus x to the 4. Okay? Let's see what happens here. So please first you do something, and then we will work on it together. Tell me what the limit is, basically, okay? Tell me what's limit as x goes to infinity and what's the limit as x goes to minus infinity. Do you understand why I want this limit? X going to infinity means scroll the graph to the right. And then you're asking yourself, what's the elevation of my graph, right? The graph has the x coordinate, and the y coordinate is given by 1 plus x to the 6th power divided by 1 plus x to the 4th power. So what's the limit? Infinity. Okay, the limit is infinity, guys. Did you all hear? Do we have a horizontal asymptote? Limit is infinity. Well, do we have a horizontal asymptote or not? No, naturally not. Because that means my altitude is what? As I move to the right, my altitude is doing what? It just grows and grows and grows, right? So I'm definitely not traveling on a plane or on a horizontal line here, right? The reason I say plane is I'm actually thinking of a very nice Russian poem. It means, and I'm thinking you are in the smoke of the train and always fields and fields. You know this? I should teach you those things as well. Я в дыме поезда, поля, поля. Very famous. So look what I do, guys. I factor out x to the power of 6 from the numerator because that's the highest power I can find in the numerator. You see? And that's what I get. Do you agree? 1 plus 1 over x to the 6. Good? And I factor the biggest power on the denominator, x to the 4. So I have 1 plus x to the 4. Yes? And then when I cancel them out, they don't fully cancel. This becomes x squared. Yes? It's x squared times 1 plus 1 over x squared over 1 plus 1 over x to the 4th. So it's really like this part, this fraction looks almost like 1, and this goes to infinity. Yes, Christina, y equals, but not quite y equals y squared. We're getting there, right? So when you say an asymptote, we're just saying some familiar shape, okay? So that's very, very flexible term as far as I'm concerned, you see? So you have, in the standard terminology, you right away think asymptote is some sort of line because that's the easiest shape and everybody is familiar with lines, okay? So you say usually horizontal asymptote or oblique asymptote, but in this case, Christina, you see, anticipate what I'm gonna say. The graph will look like a quadratic, not necessarily x squared, but something very similar to an x squared. And that's what we are going to find out in a moment. Are you ready? Okay, so if you, and then I do long division, guys. I'm afraid to even ask, do you know how to do long division? No, right? Well, I hope yes. Okay, so here is long division. We can talk about how to do that after class if you want a refresher. So here is what I do, guys. So you see, I write this type of thing. I write x to the 6 plus 1. I write this division sign, and I write x to the 4 plus 1. And then what I need to do here is I need to figure out what to multiply x squared to get rid of the biggest power. So clearly I multiply by x squared here. Do you agree? I multiply by x squared, so I write what I multiply by. So it's x squared. Now x squared times x to the 4 is x to the 6 times 1. It's x squared. And then I subtract. You see, I take this and I subtract. What it achieved is I got rid of the biggest power. Now I'm at minus x squared plus 1. You see, I take this 1 and I just take this minus that, and that's what I write here. Minus x squared plus 1. Now I can stop here. Look at it. I can write x to the 6 plus 1 over x to the 4 plus 1, and that equals to x squared plus minus x squared plus 1 over x to the 4. And notice that this limit, no matter if I take to plus or minus infinity, this limit is disappearing to 0. Do you understand what that means? It means that if my value x is very large, either in the right direction or in the left direction, this is called perturbation, or this vestigial thing, this tail, this vestigial calculation becomes almost irrelevant. Do you understand? Because it's like x squared plus a number that's close to 0. So for large numbers, it's like the number squared plus something that essentially looks like 0. Do you understand what that means? That means that my graph looks like y equals, well, x squared is not negative, x squared is positive, right? What you mean, where? What you mean in this calculation here? That's because I subtract. Look at this line. I subtract from it x to the 6 plus x squared. Subtracting x to the 6 from x to the 6 is 0. Now, subtracting x squared, you get minus x squared, and then plus 1. It's just because you take this line and subtract from it this line. Good? Well, in theory, Christina, right? So pre-calculus class, everyone should know it in theory, but in practice, I do everything I can to make the class self-sufficient. But you have to help me, guys. Do you understand that? Here is the thing. You see, the statistics for this class you have to know, right? So with me, people fail maybe at 30%, and that's because I'm nice. like 60% to 50%, you know, of fail on average in such classes, especially in Calc 2. And why? Because you don't have the background or don't put enough hours. This is, make no mistake, a very work-intensive class. You spend, if you don't understand something, you stay after class. And you stay until I leave. Good? And you practice at home, hours upon hours of solving it. If you haven't opened the question, that's very bad, guys. Good, so what we have here is x squared plus this thing. And this vestigial tail disappears to 0, which means, do you imagine it, guys? It's quadratic. I'm just squaring the number and adding something very small to it. Yes? So the graph is going to be the asymptote, as Christina predicted, is in this case x squared. That's my, I call it quadratic asymptote, okay? Now your next assignment, guys, is to figure out what happens here. Do you see this? We have a rational function, x to the 5 plus x to the 4 minus 4x cubed plus 1 over this expression, okay? Did you write it down on a piece of paper? I want to give you a plot of that graph so you see what happens, okay? So just you have a better feeling when I show you a picture. Calculate whether or not this graph has asymptotes, please. All right. How are we doing? What's the limit as we go to infinity? What are the asymptotes? Let's see where we are. 2 more minutes. Okay, here we have the first candidate. Okay, thank you, Kimira. Beautiful. One more minute and we do it together. Zvi, beautiful. All right, we had 3 answers. They all agree. Let's see what we do, guys. Here is my situation here. So do you see what I do? Maybe one time we will do it together. Let's do the calculation together so you see how that works. Okay, ready? I'm gonna do it side by side. So here is how I begin. So here I write the expression I want to divide. And here I write what I want to divide by. What do I put here? Look at it. I have x to the 5 and here I have x to the 4. X to the 4 must be multiplied by x. So I write here x. Now once I put an x here, I multiply it right through. And what do I get? I get x to the power of 5 minus 4x to the power of 4 plus x. Yes? And here I subtract. The goal was, look at it, I now removed x to the 5. So now what do I have? I have x to the 4 minus 4x to minus 4x to the 4th. So I have 4x to the power of 5. Oh, sorry, 5. X to the power of 4. Yes? And then what? And then minus 4x cubed minus x plus 1. Do you see how I got it? Everybody understood how I did it? Just subtract. You see this thing, from it you subtract this thing. So the minus is multiplied by each, and then you just add. You understand, guys, what I'm explaining, right? You subtract one thing from another, multiply the minus through the lower line and add. That's the same thing as subtracting, right? So we have this. Now, what's the next thing I need to do? Look at it. It's 5x to the 4. I can multiply x to the 4 by 5. Yes? And so what happens next is then you will get this line and you continue calculating until the power that remains is too small. It's smaller than x to the 4. Good? It's easy, right, guys? You repeat. I hope you think about and understand why this process works. It's very simple, right? You're just reducing the degree. And then what? And then you see that the result is x plus 5 plus, look at it, the power of the numerator is smaller. Do you see that? Which means that this expression will go to 0. Do you agree? if I factor and do this, this is this vestigial part, this remainder divided by x to the 4 minus 4x cubed plus 1 will go to 0, either to plus or minus infinity, which means if my number is very large, I essentially only care to calculate x plus 5. Yes? And what does it mean? It means that my graph will look like a slanted line. Let's look at the graph for a moment. You see, look at this picture. The graph is very complicated here. Do you agree? Now, we move to the right and look. Do you see what I'm observing? It looks like a line. It's just not horizontal. Do you agree? Now, maybe you remember what is a vertical asymptote, right, guys? Do you remember that if the limit does not exist, there is a vertical asymptote? The reason it's called vertical asymptote, do you see this line? It looks like a vertical line here. So is whatever you learned about asymptotes, that they don't intersect or something like that, the curve does not intersect the asymptote, that's complete nonsense. Okay? In vertical asymptotes, because it's a function, basically a function cannot intersect its vertical asymptote. But that's because it's a function. Okay, you think about it, right? But what we speak about when we talk about asymptotes has nothing to do with intersection. It has to do with what the graph looks like. Clear? Here is basically, now we are going to learn how to do this operation very fast. I call it think in the box method. So usually I tell you think out of the box, but here observe that if I have any rational function, all I have to do is just look at the leading coefficient together with the power divided by the leading coefficient together with the power. So the result will be simply the same limit as if you just ignore everything else and just look at the leading terms. And why that's true, it's because I can carry out this calculation once for a generic function so that I don't have to repeat this thought process anew for each problem. Do you see what happens here, guys? Look at it. If I have this expression, I just factor leading power x to the n, and every other coefficient is divided by at least x. And I do x to the m for the denominator, every other coefficient except for the leading one is divided by at least 1 over x. So that means that when I push the limit, this fraction approaches an over bm, whereas this approaches the limit xn over xm. So that means that I can ignore everything else. So very quickly, guys, without doing too much effort, you see this? I want you to tell me what is the limit for A, B, and C, and tell me if you think you will have horizontal asymptotes or other type of asymptotes. You don't need to calculate them. I just want to know what's the limit at infinity or minus infinity for any of the expressions there, and very fast. So write A, what's the limit? B, what's the limit? C, what's the limit? Okay, Humira, good. 1/2, right? So A, you can write them all together, guys. If you did it, so to avoid clutter, write the solutions for all of them, right? A space B solution space C solution, so I can see at all of them right away. Okay, even if you wrote already for A, write for all of them A, B, C, and I will look at what you are saying. A WhatsApp group for this class. I mean, so you can work together on the questions on my exam. That's a good idea. Yes. All right. Here we are, guys. Look at this A. A is wonderful. I see a lot of you are getting it. Guys, do you really get it, right? Not just the calculation. Isn't it very easy? Factor numerator, factor denominator. Do you see that everything but the leading terms don't matter when I push to infinity or minus infinity? Yes, because what's the idea? In the rational function, if I see the highest power of x and I factor that out in the numerator, every other power of x I see is now, we have a division by x at least, right? It's either 1 over x or 1 over x squared, and those things will be disappearing because when x is large, 1 over x is tremendously small. Good? So they will be, they will disappear. So what do I see here, guys? Look at it. This is what I do. I look at the leading coefficients. I simplify them. I see 1/2. I look at the leading coefficients. I see that the answer is plus minus infinity. By the way, this 1/2 is what? Do we have a horizontal asymptote in the first example? Do we have a horizontal asymptote? And if so, what's that? That's y equals to 1/2. Do you agree? It means, do you understand why? This is just the second coordinate of my graph. When you see the picture and you see it's meandering curves, you're just comparing x with the altitude calculated by this function. The function is only the altitude. It's not the graph. People are mistaken when they think that that the graph I show is the function. You see, guys, when you look here, look at it. You see this curve that you are seeing is not this. The curve you're seeing is x comma this function. The only the altitude is the function here. Good. So then the middle thing is plus minus infinity. You can see that there would be a curved asymptote. So what sort of asymptote do you expect for B? Would B look like a line or not? Well, careful, it will look like a line if I push to plus minus infinity or not. What will be the slope of that line if so? So do you see that 6 over, so this kind of looks like 2x, do you agree? Kind of, be careful, it looks like 6x cubed over 3x squared, so it kind of looks like 2x. So it will be a line of slope too, but there will be also a coefficient that I can calculate by long division. You understand? It will be something like 2x plus a number. Do you see that? Because essentially 6x cubed over 2x squared, or 3x squared, sorry, right? That is like 2x. So that means that we are going to have a slant asymptote. Clear? The power determines what sort of, in here, the limit is 0. Do we have a horizontal asymptote? Yes, and that horizontal asymptote is y equals what? You see, guys, you should right away. I'm hoping that if you're not responding, that's because it's too obvious to you. Y equals 0, right? So we have the x-axis is the horizontal asymptote here. Yes, good, clear. Now again, let me remind you what is a vertical asymptote. Okay, a vertical asymptote occurs in the following situation: if limit as x goes to a plus or a minus is plus or minus infinity, we say that the function has a vertical asymptote x equal to a. Now you see I drew you a picture, right? And vertical asymptotes, the function cannot, usually cannot intersect, right? But that's not very important part. I mean, don't worry about can it be intersected or not. Just understand what's the situation, right? When you take the limit, look at it, the function approaches infinity. As you get closer to, let's say, x to a plus, the curve just shoots up. In this case, when you go to x minus, the curve shoots down. The point is that this shooting up curve looks like like a vertical line. That's why you call it vertical asymptote. Do you understand? It's really this picture that you're looking at. In this case, there is some number somewhere between 0 and 1 that makes this shoot up. Do you see this? You see this curve? It looks like a vertical straight line. Or if you go here, it looks like that same vertical line. You see, there is a break, but it looks like a vertical line. That's a vertical asymptote. That's nothing special there. Just that the picture looks like a vertical line. Okay, find the asymptotes, both vertical and horizontal, of this expression of root of 2x squared plus 1 over 3x minus 5. Now notice it's root. So that's now an algebraic function, the most general type we have yet studied. You see this? I hope you can see the screen. I don't in the screen. I don't want to scroll. If not, let me just maybe draw it here. Good. So help me find the asymptotes. Come on, guys, fast. So write x equal to 5 over 3. That's better, yes? So here, let's begin doing it together, guys. Okay, so let's try to see what happens here, guys. Okay, so let's first consider what happens if I push x towards 5 over 3 for plus or minus. You see? So if you do it slightly more than 5 over 3, you get plus infinity. Do you see why? If you plug 5 over 3 into the root, into this expression, you get some number. And here, a positive number, in fact. In here, you get 0. So if you push above 5 over 3, you get plus infinity. Below 5 over 3, minus infinity. So that means that the graph has to become vertical near the point 5 over 3. We have a vertical asymptote there. Now, if I push to infinity, look, I can do the same thing. Push to infinity. Be careful there, push to infinity. I factor inside of the root, I factor the biggest power, x squared. Do you see that? And here I factor the biggest power, which is x. Now I know that root distributes through each part. So it's really root of x squared times root of 2 plus 1 over x squared divided by this expression. Now here I make an extra step. Look at it. I put a root of x squared is absolute value. Do you understand that? It's not actually x because it's absolute value. Look why. So if I were to, let's say, take the root of minus 3 squared, right? I do not get minus 3 because that's my x. What I do get is absolute value of it. That will be important in a moment. Do you see that? So a lot of people do the following incorrect calculation. They say root of x squared equals x. Now this is very incorrect. Okay, root of x squared is equal to absolute value of x. Where are you lost, Francis? With the root? Here. What is root of x squared? Let me just see, guys. Root of x squared, tell me, what do you write? Okay, absolute value of x. You understand? So Robert, you say x, and you're, again, root of is, look at it. If you're claiming that this is x, what is this x representing? This means that if you take a number, let's say here is a number. You see, what's my x? My x, if you do this, my x is this number here. Yes? Because that's the number squared. Is it equal to -3? Because that's my x. And the answer, obviously not, right? The answer, it's not equal to -3. Do you understand? That's why root of x squared is not x. That's going to be very important. And Francis, I will explain your line in a second, right? So you see, it's not true. But what is true is that if you put absolute value, that would work. Because look at it, root of -3 squared is equal to root of 9, which is 3, which is absolute value of -3. Okay, so you need to put absolute value when you cancel things out. That's the first comment, right? Now, Francis, let me just go back to that previous situation. And people make that mistake all the time. I'm going to show you that it can be a costly mistake. Okay, so first, where did I get the 5/3, Francis? Well, this expression will have a vertical asymptote whenever denominator is 0 that cannot be cancelled. Right? So if numerator can be processed, it can process any number, right? If I square a number, multiply by 2 and add 1, I get a positive number. The square root of any positive number can be calculated. Yes? So numerator always works. Now, in the digestive process for this function, it's a digestive process. You understand? The number is processed. Denominator will not, well, denominator is going to produce 0 if I put 5/3. Understand? I am interested in this situation. When is 3x minus 5 0? That's when x equal to 5/3. You agree? So if that happens, then I get 0 in the denominator. But numerator, no matter what number I plug in, it's positive. You understand? So if I plug a number close to 5/3 instead of x in the numerator, I will get some positive number. Whereas in the denominator, if it's 5/3 plus, if it's plus, it will be 0 plus on the bottom. So a positive number over 0 plus is infinity. And if I approach 5/3 from the left, that would be numerator still positive, but denominator will be 0 minus. Are you following me, guys? Think about it. You see, think about it, Francis. Plug a number slightly less than 5/3, you get a negative number. If you plug a number slightly more than 5/3, you get a positive number. But in both cases, they are very similar to 0. So it's like a number. In the numerator, I don't even care, don't even bother investigating what that number is. I can, but I don't really care. It's just a positive number. Positive number divided by something close to 0 will either always be either plus infinity or minus infinity. Are you with me? All right. If it's plus infinity, okay, why vertical asymptote? Good question. Guys, now explain to me why plus infinity or minus infinity will make it a vertical asymptote. Do you understand, first of all, that the limit as I approach 5/3, depending on the side from which I approach, would either be plus or minus infinity? Yes? If I approach from the left, it's minus infinity. If I approach from the right, it's plus infinity. Make sure you see that. Now, if you see that, why does it make it a vertical asymptote? Are you clear with my question, guys? Well, it depends, no level, right? It depends. I mean, you see, don't try to find some sort of procedure. I'll tell you, ask yourself what makes it look like a vertical asymptote. Look at it. Do you see this? The function is growing. Now, if it's growing, where can it go, right? Look at it. As you approach this point, it is just this curve. Whatever it's doing, it's just becoming larger because altitude is getting larger. Now, if it's getting larger near this point, it will look like a straight line, like a vertical straight line. That I hope is fairly clear to you. Right? Look at it, because in this interval, you get a little closer and the graph has to explode upwards. So what can it look like? It's just exploding upwards and upwards and upwards. It's lining up, so it can only look like a vertical line. You understand? Because it's like leaning on this dashed line. It cannot touch it, because if you're approaching, you're just getting close to it. When you get and you explode, right? What can it be? The shape looks like a line. I hope it helps. Okay, guys. So let's go back to the calculation. Do you see what happens here? So first, I want to know what happens if I go to root 2 over 3. If I go to the right, you understand when I say x going to infinity? It's like I'm looking at the right side of the equation. Yes. Let's see if I can even graph it. All right, so are you there, guys? So what happens if I push limit as x goes to infinity? Do you see what's happening now? All right, so I factor out x squared. So I have root of x squared, root of 2 plus 1 over x squared, yes? Now, root of x squared is absolute value of x, but x is positive, x is going to infinity, yes? So the absolute values the absolute values are not required. I can drop them. So it's just simply x. Yes, simply x. So I can cross out the x's and I'm left with root of 2 plus 1 over x squared over 3 minus 5 over x. Now, that would be just root 2 over 3. So I have a horizontal asymptote root 2 over 3, y equal to root 2 over 3. Are you with me? Yes, good, right? Now, if you are with me, tell me what happens if I move to the left. Further and further to the left. Tell me what's the limit if I go to the left, please. Okay, maybe so. Okay, so give me the answers, guys. Tell me what happens if I move to the left precisely. Very good, Zvi. Wonderful. So you understand what happens there. The calculation is the same if I push limit as x goes to minus infinity. Do you all see that? All the steps are the same. Let's look at it carefully, guys. Let's see why it becomes negative. So you see all the steps are the same. X going to minus infinity, right? So x is negative. So I have this at this stage. I have root of x squared times root of 2 plus 1 over x squared. I hope you understand that part, yes? I factored out, and then I simplify root of x squared, I write absolute value of x. Make sure you do that, otherwise you can cause yourself problems, right? It's not, root of x squared is not x, it's just absolute value of x. Now, absolute value of x makes x positive, do you agree? Absolute value is supposed to make x positive. Now, how can you make x positive? First of all, x itself, is it positive or negative? X is positive or negative, guys? Help me, please. A lot of you are confused by this type of thing. Yes, x is negative. And if I multiply x by -1, look at it. A lot of you think minus x, and you would have said minus x is a negative number, but that's incorrect. Unless, if x is positive, minus x is negative. But if x is negative, minus x is positive. Are you with me? Are you with me, guys? Minus x is not negative, as you might think. Oh, I see a negative in front of it. No, x is a number. Depending on that number, right? If this number is negative, then minus x is positive. Minus times minus is plus. Do you understand? So just not to be confused. If you see minus x, it does not mean the number is negative. In this case, minus x is positive. So absolute value does the same thing as if you multiply the number by -1. The absolute value tries to make the number positive always, right? It doesn't have to do anything if the number is positive to begin with, but if the number is not positive, then you can multiply by -1 and the number will become positive. Good? So the thing is, good? Do you see that, I hope? So absolute value of x, because x is negative, is minus x. Not, you see, I put it. It's very important, guys. And then I can cross out the x, and I'm left with the same thing, but with a negative on the in front of the root. So it would be minus root 2/3. Good? It's very simple. Just keep just a small understanding that x is not a negative number. And here again, I try to explain to you why. Absolute value of x squared is x if the value of x is bigger than 0, but it's minus x if x is less than 0. Do you see that? You need to put a negative in it to get rid of it. All right, here is our next task, guys. Now you want to calculate root of x squared plus 1 minus x as x goes to plus infinity. Look at it, you see? Root of x squared plus 1 minus x as x goes to plus infinity. All the way. Good luck. Calculate. See what you can do. No, Robert, it's not 0. And later on, guys, if you're gonna be good, I'll teach you how to see it right away. And I'm even if you're bad, I'll teach you how to do it right away, right? So the answer is 2. If you are doing it right, the answer should be, no, sorry, what am I saying? The answer should be 1/2. I'm, by the way, telling you nonsense. The answer is 0. Yes, right? I just looked at it sleepily, right? So yes, the answer in this case is 0. I'll show you later in a moment, right? Why? Okay, let's do the calculation together. Okay, so again, some people go about and try to solve it this way. So they think, okay, the root is infinity minus another infinity, so infinity minus infinity is 0. Yes, you can multiply by the conjugate in this case, but I'll teach you later a better way. So that I'm not doing the conjugate, and I can tell for much more complicated functions what the answer is, right? So here we have infinity minus infinity. People say it's equal to 0. Could you tell me what's wrong with this reasoning? So if you did something like this, you look at it and you say, well, I'm plugging a very large number instead of x. So x squared is a large number plus 1, it's a large number. Take the root of it, it's a large number. So large number minus large number is 0. Or infinity minus infinity is 0. Exactly, it's not a number. You're in fact, maybe the way I even said it, it's already should be indicating it, right? This just means I have a large number minus another large number, but it doesn't tell you how those large numbers compare to each other. You understand? If I take large number minus another large number, which is larger, right? Are they the same or almost the same, or one is much bigger than the other, or you understand, right? This is just saying we're dealing with a large number. From a large number I subtract another large number. It's very unclear what happens. We need to investigate. So we multiply by the conjugate. You see, guys, we multiply by the conjugate. You see, why do I do that? It's because it looks like a minus b. Now, if I multiply it by a plus b, top and bottom, I really multiply it by a plus b only to simplify the numerator. But I cannot change my expression, so I need to divide by the thing I multiplied by, because they cross out to be 1. Yes? So when I multiply it out, I get x squared plus 1 minus x squared, because I get a squared minus b squared. Good? And what I'm left with is 1 in the numerator, root of x squared plus 1 plus x. So the answer is 0. Yes, as somebody said, and I said incorrectly, I accidentally said the answer will be 1/2, but you will see maybe, how I do it later on. Okay, what is it that I'm doing? I'm not actually doing any algebra when I look at it. I do something that I recognize. I ask myself, and that's what you try to learn. I ask myself, what am I really looking at, right? What is this thing about? So we don't have yet enough information for you to figure that. Okay. Now, on the other hand, if I push x going to minus infinity, look at it. If x goes to minus infinity, there is no ambiguity, you see? So if x goes to minus infinity, this is infinity. And minus infinity times minus 1 is another infinity, do you see? So if to say infinity plus infinity is equal to infinity, there is no ambiguity whatsoever. Do you agree? Because it's large number plus a large number will always be a large number. Good? So the other part, I can actually solve this way. I can say it's infinity plus infinity equal to infinity, because it's clear what's happening. Okay, let's see how good you are, guys. Look at it. Calculate limit as x goes to infinity of root of 4x squared minus 3x minus 2x. What happens now? And if you want to, I can tell you the number right away without doing any calculations. You believe me? Do you want to hear it, or you want to calculate it first? No is unclear, so you don't want to hear it, okay? That's right, Christina. That's right, Humira. That's right. That's right, Mariam, Lever. Very nice. I'll wait a few more moments. Come on, guys, come on. How long does it take to calculate it? Fast. Okay, here is another answer. Good, good, Robert. Good. Okay, guys, so you see, at most I have right now 10% that answered it. You should train to answer those questions very fast and think about it initially, right? So you can, of course, carry out the calculations by multiplying by conjugate, and you will get the number to be equal to -3/4 as x goes to infinity, okay? So how you do that, just multiply, look at it, it's root minus 2x, so you might want to multiply by root plus the other expression because you recognize a minus b, you want to have multiplied by a plus b. That's by the conjugate. Good? The answer is -3/4. Now, here is a challenge question, guys. Don't worry if you cannot calculate it. Let me just show you. the idea here is this, guys. If you do it my way, the subject is easy. If you do it some other way, my way meaning you think about what the thing is, my way was very easy, and your way will be slow if you are not thinking about it. So here is the question, guys. You see, it's the cube root of 8x cubed minus 5x squared minus 2x. Okay, now I'm gonna sit here. I know the answer right away. I look at it, I right away see what it is. Okay, look at it, guys, and tell me what the answer is, if you can. Okay. I will. I cannot do it today because you haven't learned some ideas, you understand? But we will spend a long time talking about the main part of this class. It's derivatives, or as they are known in German, Ableitungen. So we will talk about those things. So the answer to this question, let's say how I do that is this. So the answer to this question, first of all, would be careful, guys. So some of you said minus 5 over 8, right? Maybe you try to guess. The answer to this will be, you're correct about the numerator accidentally. It's going to be minus 5 divided by 12, I believe, divided by 12. So it's minus 5 divided by by 12. Here you go. I'm right. And the reason I hesitated is just because I'm very bad at arithmetic. You understand? So, right, very basic arithmetic. I can just right away see the answer. And why? It's not because I do any calculations or multiply by conjugates. It's because I think about what's written there and I think, why is this problem not immediate and what is it really about? Kind of like imagine that this is what I teach in analysis. You understand? That's why in probability. Why I like some things like this is because here is my simple example. So imagine I say something like 1 plus 2 plus 3 plus 100, right? And I ask you to tell me right away what's the answer. You know how I solve it, guys? So I right away know the answer is 100 multiplied by 101 divided by 2. And the reason I know that so fast is because I think about it, it's like people are talking behind my back. He has a younger brother and I cannot tell whether he's 2 years old or all the way to 102 and 101. You understand? Like they're talking about him, they cannot tell my age. Am I very old or am I very young? And I have and they said, and he has a younger brother, right? And because I realized that that's what it's talking about, I right away can translate the code, and that's why it's so exciting. Do you understand what I mean, guys? If you do mathematics, it's as if like you're reading someone's secret message, right? And so the reason I solved this problem so quickly is because I realized what could be that secret message. What's even more interesting about mathematics is that the secret message has simultaneously very, very different sounding interpretations. You understand? I can see within the same message many meanings, and that makes those meanings through that message somehow the same in the eyes of God, if you like to think this way, right? So when I was studying abstract algebra, I thought that you have this feeling that to God, whether you get a present, as in a flower, or whether you get shot, it's exactly the same thing. And that reminds me right away of the cemetery in Prague and how Rabbi Löw, if I pronounce his name correctly, how he died. He was a very wise rabbi, and death came to him from a flower when he smelled it. Good? So again, guys, the point is you think, you don't memorize, and if you are able to do that, if you're able to force yourself to love even the boring parts here, you will understand the subject it will be very easy for you. It will be second nature. Okay, guys, we have a little bit of time to return to paradoxes, to return and think about why infinity is such a strange thing. In the other class, I actually already had very interesting comments about it. So one of the most famous paradox about infinity, it's called Zeno's paradox. And Zeno made an argument about the impossibility of motion. Like you see every day, you see things move around, but Zeno said, no, motion is impossible. So according to Zeno, for instance, that I used to do it when I do it in my class, I just tell my students, well, there is no way you can leave my classroom. You cannot do that. And why can't you leave my classroom? Because, well, let's look at it. Right here you are, guys, and you're trying to leave my classroom you want to get to the door, but to get to the door you have to get halfway the distance. Do you agree? But to get to the half distance, you have to go through half of that. But to go through half of that, you have to go through half of that. In other words, to 1/8 the distance, and then half of that, and then half of that, and half of that, which means that with every single step you take, you should be taking infinitely many steps. And how can you do that? So therefore, you cannot leave the room. Motion does not happen. Okay, and I mean, you might think, well, that's nonsense, maybe, right? Because you will go and leave you open the door and you leave. You're not thinking about it necessarily the right way. So first of all, if it's nonsense, why is it nonsense? Okay, do you understand this paradox, guys, so far? And I'm going to try to show you, let's see if I'm right or not. So first of all, do you understand this paradox? Do you agree that motion is impossible? You can say obviously you don't, or obviously you do. It's up to you. And guys, I don't care. Just let me know what you think. Do you understand the argument of Zeno, right? So he says, that's one version of it, that you cannot leave the room because to leave the room, you have to go through half the distance. But to go through half the distance, you have to go through half of half, or 1/4 distance. But to do that, you have to do 1/8 of the distance. And to do that, 1/16 of the distance. And to do that, 1/32 of the distance. You understand? And so it seems that you have to take infinitely many steps. Do you think that Zeno is right? Okay, Angelo says no. And how can we solve this? Or say, so we will see first of all if you agree. I want to see a baseline. What do you think right now? Is it wrong? Can you get to the door? Is there a problem here? So no means no problem, or no, you cannot get to the door. Oh, you see, Robert, you should read Pushkin, because there is a poem called "Движения нет, сказал мудрец бородатый," which means motion does not exist, said a wise beerman, and the other guy just stood up and left. You understand? So it's kind of like this. I remember in high school, well, in the ancient time when I was in high school, I once spoke about something from Kantian theory, and I said time and space are intuition a priori and do not exist. I was very much Kantian, and there was one girl, very I would say of common sense type of girl, and she got so annoyed she stood up and left the room. Right, when I said that. And funny enough, I remembered her, and I thought, well, here is a simple girl, and she's not bothered by such things, and who knows, in your wisdom, you can get into an intractable forest, right, and reach conclusions that are absolutely incorrect through very, very, very complicated thinking, right? And for her, life is very simple. It's black and white, up and down. She knows where up and where down is. where left and right, and I never do. You know what I do when I drive, guys? Very dangerous. I say left. I have to, if you tell me suddenly turn right or turn left, I usually turn wherever I want, because to me, right or left is already where I decided to turn, right? And so when I have to do, when I drive, I say left is where my heart is. Left is where my heart is, but where is my heart? I don't have it. You see, I lost my heart. So this is this problem, okay, guys? What's stopping you from traveling? That's very interesting, Jen. Exactly. What stops me from traveling infinitely many steps? That's a very, very good question. We are going to analyze it a little bit deeper here, okay? I hope you will enjoy it. So, guys, so here is a universe creation experiment. Very simple experiment, but let's see what you think about, right? Let's pretend, as they said, Vayomer Adonai Yehi Or, right? And there was light. Let's see if we can do that. So we are going to recreate the stars in a particular way. So here is what you're going to do, guys. Imagine that the stars will create infinitely many stars, and they are numbered integers 1, 2, 3, 4, and onwards. They are numbered as the whole numbers, okay? Are you with me? There are going to be 2 creation experiments. Creation number 1 is the following. 1/2 minutes before 12, you have stars numbered 1 through 10 appearing in the universe, with star number 10 immediately extinguished. Do you see what happens? So star number 10 immediately extinguished. Now, 1/2 minute before 12, how many stars I have in my universe? Clearly, I have 12. Sorry, I have 9 stars. Yes, 9 stars. 1 extinguished. Ein Stern wurde gelöscht. 1 star disappeared. Yes? Now, 1/2 squared, a quarter minute before 12, the next batch of stars appear in this universe. Stars numbered 11 through 20, with star number 20 immediately disappearing from the universe, immediately extinguished. That's the situation. Help me, please. So the number of stars 1/2 squared minutes before 12 is, well, 9 times 2. Right? We want to keep a formula. So I don't care that it's 18 as much as I care that the pattern is, well, it's for something else. It needs to immediately expire for me to illustrate some interesting point. Okay? So bear with me. It immediately expires. We have 9 times 2. Look at it. 1/2 to the power 2. 9 times 2. Now, guess what would be the next time interval where something is happening? Next creation step is at what power of 1/2? Type in the comments. 3. And that would be 1/2 to the power of 3. Do you agree? That's 1/8. I just do it neatly in powers of 1/2. 1/2 cube minutes before 12, stars numbered 21 through 30 appear. Star number 30 immediately vanishes, immediately is extinguished. Good? So how many stars I have in my universe? 9 times 3, do you agree? Because I had a net gain of 9 stars. Are you with me? Okay, Robert, well, that's too bad you're leaving, but you know, if you want, you can join in the evening, okay? Or watch the video or whatever. Okay, guys, do you understand? Now, you see, we want a general pattern. You understand what's going to happen? Now, 1/2 to the power of n. All that means is just I want to describe just an arbitrary step. Arbitrary step. 1/2 to the power of n, where n is 1, 2, 3. At the 1/2 to the power of n step, what happens is that the stars numbered 10 times n minus 9 all the way to 10 times n come into existence, with star 10 times n immediately vanishing. You understand? So you can see how it works, right? First step, when n is 1, it would be the 10th star vanishing. When n is 2, it's the 10 times 2, which is 20th star vanishing. You understand? So that's the general pattern. Are we clear there? Now I will need you to tell me, please, at 12. We will answer it. That's just experiment 1. At 12, how many stars do we have in the universe? once I reach 12? How many stars? Infinite. All of you are saying infinity. Let's see, 2 people right away react and say infinitely many stars in the universe. Do you agree with that? If so, please write it, and definitely write for yourself so you don't forget. Okay, infinity. Yes, you're saying infinity for this experiment. Good. Any other answer before I move to the second version of the experiment? Well, again, remember, Joe, infinite minus n. N is a meaningless thing. N is just it's a symbol standing for the step. What do you mean infinity minus a step? It's not a sensible answer, right? There is no such thing as n, right? I just described in step n what happens. In step n means I just described all the steps simultaneously. If n is 1, I tell you what happens in step 1. If n is 2, I tell you what happens in step 2. Do you understand? When I say step n, I just describe all the steps in one line. It's just like a code. Clear? So to say infinity minus n means nothing. There is no such thing as n. Are you clear on that, guys? It's like there is no such thing as a person. There is, when I say person, I mean you and you and you and you and every person. Right? Person is a variable. When I say you are a good person, it means that that if I look at you, you belong to all the people that are labeled as good. Clear? So truly, there is no such thing as a person. There is such a thing as Francis. There is such a thing as Angelo, as Anna, as Zvi, but there is no such thing as a person. It's just a convenience of speech. And here is Zvi. You see, Zvi. Zvi is asking something very interesting. If we keep halving the time, look at it. If we keep halving the time, do we actually reach 12? That's what Zvi is saying. You see, we keep halving the time. Half, and then half of half, and half of half of half, right? By the way, do you see, Zvi, how similar it is to Zeno's paradox, right? Because in Zeno's paradox, we are halving the distance, and here we are halving the time.
It's the same thing, just space or time, right?
Yes, same thing as having space or having time. So we're actually seeing the same paradox in some sense. We're thinking about the same paradox, but here we're halving time and not space. Good. So Zvi had something very interesting to say. We'll keep it in mind. And the rest of you, I presume you're saying infinity right now, yes? Now let's do experiment number 2. Are you ready? Experiment number 2. It's very similar. Do you remember what happened in experiment 1? So 1/2 minutes before 12, stars 1 through 10 appear, 10th star disappears, right? Basically 10th star disappears, 20th star disappears, 30th star disappears. Good. Now here is the next procedure. Experiment 2. Look what happens, guys. Exactly the same thing. 1/2 minutes before 12. Stars 1 through 10 appear in my universe, but star 1 immediately expires. You understand? Before, in previous experiments, star 10 immediately expired. How many stars do I have at 1/2 minutes before 12? 9. Thank you. You have 9. Now, 1/2 squared minutes before 12, stars numbered 11 through 20 appear, but this time star number 2 expires. Okay, it did not expire after first experiment, after first procedure, but it expired now. So how many stars do we have in the universe? Clearly, we gained an extra 10 and we lost 1, right? So altogether we gained 9 stars. So it's 9 times 2. Do you agree? Do you see my trend of thinking? That's very nice. Now, what happens 1/2 cube minutes before 12? Well, you can obviously guess that stars numbered 21 through 30 appear, but this time star number 3 vanishes. It now is extinguished. Good. And in general, at star number n, at procedure number n, at 1/2 to the power of n minutes before 12, star numbered n expires from the universe. Clear? And now my question is, as before, how many stars at 12? Is it different from your previous answer? or not? How many stars in the universe exactly at 12 a.m.? Okay, Christina says infinite, same thing for both situations. What about the rest of you guys? Talk to me. Think about it and let me know what you think. Infinite, Joe says, lever infinite. Gabi, what do you think, Gabi? Okay, so Joe says something else. Do they all expire? So
I'm a little bit unconcentrated. Sorry, Professor.
no, not okay. Well, that's my question, guys. I mean, you're asking me a question in return, but what do you expect is the number of stars at this moment? You understood this experiment? Let's see what you're saying. But none are very close to none. So, so a few of you are saying 0, I think, right? And Humira, you're saying what? None or very close to none. So Tzvi says 0 stars. Interesting. And some say infinity. So let's look at the situation here, guys. Okay. So, and we will consider other answers. One answer is, of course, that Tzvi suggested is we never reach 12. I tend to hear about such an answer all the time. Good. So first, notice that in both experiments, the number of stars gained is limited as n goes to infinity of 9 times n, right? Because each procedure gives us extra 9 stars. So that limit is approaching infinity. So that means that in both experiments, as I'm getting closer and closer to 12, the number of stars explodes and becomes infinite. It grows without bound as I approach 12. But what happens at 12 actually? Well, let's see. In the first experiment, I remove only the digits 10. You see what's the easiest way to verify whether the universe is empty or not. So for the first experiment, I can imagine reaching out into the universe and grabbing a star. Can I grab a star? Yes, I can. I can grab the star 1, 2, 3, but I cannot grab the star number 10 because it expired. I cannot grab star number 20 or 30, or any star divisible by 10 will not be grabbable. Do you agree? But every other star whose number is not divisible by Christina, and that's an amazing question. We will get there in a moment, what we are thinking about. Will we ever reach 12 is the question. Good. So we reach there into this universe, and we can hold stars numbered 1, 2, 3, 4, 5, but not 10. Not 20. Yes, so there are clearly infinitely many stars in the universe if we reach 12. Let's for now ignore the situation if we can or cannot reach 12. If 12 o'clock is reached, we will have infinitely many stars in the universe. Yes. Now, what happens in the second experiment? If you reach into that universe, can you pull out a star? Will you see a star? Well, if you did, it would have some number. It cannot be the number 1 because the number 1 star expired after first procedure. It cannot be 2 because it expired after second procedure, or 3 as it expired after third procedure, or 4 or 5 or 6, or a millionth star expired after the millionth procedure. Do you understand? It cannot be any star. And therefore the answer that some of you gave of 0 is correct if we reach 12. Yes, if we reach 12. Now, to address the problem of reaching 12, some people say you don't reach 12, but if you are saying you do not reach 12, then you are a member of the Zeno club. You understand? I think, because then you're saying you cannot reach the door. Good. You see, because in the Xenos paradox, what are you doing? You are dividing space into infinity segments. You take half of space, 1/4 of space, 1/8 of space, and onwards, right? And here we take the interval of time and we divide it into half, 1/4, 1/8, same thing. You understand? So, of course, you can argue that space and time are not the same thing, even though naively they are so represented. So yes, I would say that if you are thinking about intuitively, then intuitively it's your job to carry out the procedure when the procedure is required, and time does not care for what you do, right? Time flows, at least that's metaphysical. We're talking about metaphysics here, right? It might be absolutely wrong, but time can flow in any, basically indifferently to what you're doing. Do you agree? Time is indifferent to what you're doing. If you believe that, like in Kujava's poem, and time is a careless coach rushing the horses forward. А время торопит возница беспечный и просится коней в полет. So the time does not care, perhaps, what you are doing and how it affects you. And then carrying this procedure, if you can carry it out, will not affect time. Okay? And there is no reason, at least no easy reason why you cannot move through infinitely small segments of space, similarly to that. Although you can take relativity theory, right? And that's a very non-intuitive and deep consequence, is that if you approach the speed of light, you understand, if you want to carry this procedure by actually moving things in and out, you will eventually have to move faster than the speed of light, and speed of light is constant. Let me, by the way, ask you a small question about the speed of light. Maybe you know, and maybe you do not. So most stars are located many light years away from planet Earth. So let's say you're looking at a star that's located 4 light years away from Earth. You know what it means? Is that if you send a beam of light, it will take 4 years for that beam to reach that star. That's what it says, right? So imagine now you're traveling at the speed of light to that star. How long will it take you to reach the star? What do you think? If you're sitting into a space shuttle and you are told that you're traveling to a destination that is 4 light years away from Earth, how long do you think it will take you to carry the journey if you're inside of this spaceship and you're traveling at speed of light? What do you think? So a lot of you say 4 years, right? Well, 4 light years, and you're traveling at the speed of light. So the answer is actually, if you sit on that star, time will stop for you. It will be instantaneous. It's only for people observing the light from the side, from Earth, that they would think it took you 4 years. So if you are traveling to a star that's 1,000,000 light years away, if you're traveling at the speed of light, it will not take any time whatsoever. You right away be there. But if you are watching the light ray travel there from Earth, it would look to you like it takes whatever, 1,000,000 years. That's the thing about it, right? So, but that's more complicated. You get more complicated. And you see here, I even wrote that quote, which I immediately think whenever I speak of this paradox or of time. And time is rushed by indifferent driver, and horses ask to move forward. Okay, that's what I just said. Now let's look a little bit deeper into Xenos Paradox, guys. Are you still with me? Are you exhausted entirely, or can you pay more attention? We just have 20 more minutes to go. Are you with me? You can hold, or do you need a 5-minute break? Christina, for you, yes, continue. You see, when people ask me all the time, what is the application of mathematics? All the time, right? What is it for? What is it useful for? Do you know I'm surprised by those questions sometimes. You know why? Because you can watch, or many of you watch football, right? I even have this one guy, it's funny, from Germany, he texts me and says, are you watching the Super Bowl? Because even he in Germany is watching the Super Bowl. And I think, so they watch this game, which is just a game. I mean, what does it matter if you win or lose, right? It's just a game. But people, some of them are obsessed to the extent that they can commit suicide if their team loses, right? Now, do you know what is mathematics really? What is the use of mathematics? If it has a use, I think one major use is it might make you more interesting people. It might make you see things that that you otherwise do not see, right? Because you have eyes, you can smell, you can eat. All those things are common to all of us. But if you study mathematics and study deeply, not just like crunch numbers and boring stuff like that, which I never liked. I mean, I didn't even think I would do that. I liked philosophy, right? It might give you some ideas, interesting ideas that you otherwise would never have had. It would make you look at this world entirely differently. Okay, and then you can argue, of course, is it sometimes you get this, desperate and you think pretty much that all your approximations are hopeless, or they are very far from anything that can be deep, right? Or you're very far from knowing the mind of God. Right, whatever that even means. And people ask even about some people ask me even you know, what I think about the religion or God and whatnot, right? And if you study mathematics, you will have a very different you might have a very different notion of those things. Some questions, when people say I'm an atheist, I don't believe in God, or I am believing in God, some of those things come from ignorance. So like basically usually what I think that what one says and what another says is meaningless. Right? If you think about it deeply, it's completely meaningless to say I'm atheist or I'm religious, usually very meaningless. And in mathematics, you have some sort of interesting insights. So let me now talk about this, guys. Let me now talk about Xenos Paradox and make it even worse and more confusing. I do not know if you believe in motion, but basically, I basically sinned a lot in my life, and I was punished for it, and I'm in hell, eternal hell. Now, let me explain to you what is my hell. My hell is the inability to reach that door and open it and leave. I live a Groundhog Day in which motion is completely impossible. It doesn't exist. And I dream in my dreams, guys. Let me show you what I dream of. Some of my dreams are nightmares. Some people say take ecstasy and you will see fractals. But I don't need to take ecstasy, as I see them anyhow all the time. This is one picture of a fractal that I have here, you see? So those objects are infinitely complex. Those bubbles are, how do you say that? There are infinitely many of them. And in my dreams, I sometimes fly through this thing and I try to calculate my orientation. It's like you're spinning in space and you cannot figure out where you are located. And you know that once you lost where you're located, it is forever gone, forever. That you will never find your way back. So let me try to explain to you in the simplest way what can happen when you are living in this universe. Are you ready? In my universe. So in my universe, you are an insect. And imagine that this insect is living in the simplest possible space so that we can visualize it, right? That insect lives in the space that is just this space from A to B. And imagine that in 1 second, the insect is supposed to travel from point A to point B. You can think of this as a very flexible modern screen that you can stretch if you want to, and you can fold if you want to, and the insect will not notice because the stretching and folding happens with respect to higher dimensions and not with respect to that simple region where this insect is living. Yes? So basically, if I stretch the screen, the insect will still think it's the same space and run from point A to point B at the same rate. Do you understand? No change. Now, here is going to be what I'm going to deform the space. So I'm going to stretch and fold that space so that, look at it, I stretch it in factors of 1/3. You understand? So initially, if I divide it, it has 3/3. Now I fold it and I make it have 4/3. You understand? It's like I remove the middle thirds and I replace it by 2 copies of 1/3. So you have this structure. 1/3, 1/3, 1/3, 1/3. So I have 4 fourths. You agree? How long does it take the insect to get from this point to that point? What do you say? You understand what you're watching this insect on the screen? You made the space, you stretched it, and you fold it so that it's now 4/3. How long does it take the insect to reach the other end? Do you understand what I'm saying, guys? Right? You walk on the slide, the insect, you watch a movie. Can you imagine folding the screen? Can you imagine a very flexible screen that you can stretch or compress? Have you ever stretched your video, like YouTube video? You can make it stretched or larger or smaller. Does the video play longer or shorter, or does it play the same duration? Same thing here, right? It plays the same duration. Do you agree? Right? Because if you're watching this video of the bug on a small screen, this is the distance. It takes 1 second. If you watch it on a large screen, this is the distance. And it takes 1 second for the video, for the bug to get from point A to point B. Do you agree? So if I could fold my screen like this, it will still take what? It will take 1 second. But for me, watching this screen from the side, it looks like the bug is walking much faster because now the distance is 4/3. Do you agree? The distance used to be 1 and now it's 4/3. 1, 2, 3, 4. 4/3. Are you with me? It's very important for you to follow what I'm saying to understand what happened here, right? So as I watch the bug walking on this folded futuristic screen, the insect gets from point A to point B in 1 second. Do you agree? Yes? Now, what I continue doing is now I take each of those segments now and I cut them into further thirds. And now what is this segment? It's 1, 9, 1, 9, 1, 9, 1, 9. So now it's 4 9s. And this one is 4 9s. And this one is 4 9s. And this one is 4 9s. You understand what happened here? Now, how long is this full track? Can you tell me how long is this distance now, as I perceive it? What happened here, guys? It used to be 1. I multiplied it by 4/3. 4/3 to the square. Beautiful. You see, to get this distance, look at it. What happened here? I made each length 4/3 larger than it used to be. So the effect on the full length is to multiply the previous length by 4/3. So it's 4/3 squared. Correct, Christina? Do you all see that, guys? Look at it. This used to be 1. And now it's 4/3. So how much longer is the new shape? It's 4/3 longer. Now here, look at it, right? I introduced those segments, but what did I really do? I made this segment longer by 4/3. Do you agree? I multiplied it by 4/3, and this by 4/3, and this by 4/3, and this by 4/3. So it's 4/3 square. And you continue in this fashion and you continue doing it onwards. The next stage, you make it have more segments, right? This means this here, guys, I multiplied by an extra 4/3. So this is 4/3 cubed. But I continue modifying the shape on and on and on until, I mean, I can show you how the picture looks like if you prefer to see it, not from my drawing, but from the internet. So it's called von Koch curve. This is the way this curve will look. Here, do you see this, guys? Here, do you see it? Begin with a line, then this, then this, then this, and then more and more and more. Do you understand? The effect on length is I always multiply it by 4/3. Now, can you tell me how fast does the insect travel, right? So to get, if the insect gets from this point to that point, in this video, it's 1 second. In this video, how long? 1 second, right? I just stretched the screen. It's just my perception. It's the same space. It's just very contorted in my two-dimensional universe. Now, in this case, how long does it take the bug to travel to this point? 1 second again, and 1 second for all of them. So could you please tell me at the end of this process, it seems it will take 1 second. What distance do you think is traveled? If as I perceive it, if the bug moves along this curve, what distance is traveled? Infinite distance. Do you understand what I'm saying, guys? It's infinite distance if I travel along this thing. Not only along the full curve, what do you think is the distance between this point and that point? Or between any 2 points that I perceive on this graph? What do I perceive the distance to be? Infinite. Do you understand, guys? Take any 2 points, no matter how close, they are very close in 2-dimensional space. In this 1-dimensional space, the distance between any 2 points on this curve is infinity. Can you imagine that? Within that space, the distance between any of those 2 points is infinity. I can make a cut, let's say, and I can move very fast if I move through 2-dimensional space. I can go from here, for instance, to here very fast. But along this curve, the distance is infinity. So now here is that paradox, you understand? The bug, as I perceive it, is moving infinitely fast. Or maybe the bug is not moving at all. That's the problem, you see? So that's Zeno paradox. If in topology, these 2 spaces, the original space and this one are exactly the same space. It's just a distorted space. You understand? For topology is the study of spaces. Mathematical study of spaces. Those 2 spaces, the initial line and that curve, are the same. Isn't it interesting? You see what I'm saying, right? So this is Xenos paradox, but slightly more modern. I hope you understood, guys. Here are those questions. You can again look at them if that's what would you like to do. So we have 10 minutes remaining for this class. Perhaps I should tell you several things. Maybe what would you like, right? Would you like? Right? Another thing, by the way, I can show you how imaginary numbers, if anybody is interested, imaginary numbers, root of -1. Do you know why root of -1 is impossible? Or maybe it's not impossible. But if you believe in root of -1, you know how many cats I have. Or that actually I have cats because there is a root of -1. No, not necessarily. All right, so let me show you something. I just do not know if you see, so I see you begin to disappear, guys. I mean, I do not see your faces. You decided to hide from me. Should I show you what happened last semester? What was my inspiration of how to conduct interrogations of people that decided that they can cheat on my exams? Look at that, guys.
Herein.
Come in.
Hände unter die Schenkelflächen nach unten. Was haben Sie uns zu erzählen?
What do you have to tell me?
Wenn Sie wissen wollen, ob jemand schuldig ist, gibt es kein besseres Mittel, als ihn zu befragen, bis er nicht mehr kann. Stellen Sie mir noch.
If you believe that someone is guilty, you ask him until you cannot hold any longer.
Einmal, wie Sie den 28. Bei Verhören arbeiten Sie mit Feinden des Sozialismus. Wenn Sie uns den Namen nicht nennen, muss ich noch heute Nacht Ihre Frau verhaften lassen. Wollen Sie das?
In einem System der Angst.
You got the point. That's, by the way, a very good movie. So if you ever want to see it, it's called Life of Others. Very good movie. So you see, guys, I hope none of you think that the class is hard and that you will be, lying to me. If I think that you are lying to me, I will talk to you like in that movie. right? And I cracked people, so I made them admit, not only that I had proof, I made them admit. I will use everything, psychological warfare and everything else, but I would be very annoyed if I need to do that. So don't ever cheat. Understood? Other students did not listen to me last semester. In probability, half of them, because I thought they are, I can trust them since they're math majors, decided to copy solutions from the internet. I might not catch you, that's true, because maybe I will be too lazy, right? First of all, you have the final exam. There are some very good technological tricks to catch you. And in my exams, don't be tempted. Okay, now what do we want to do, guys? We want to begin solving some practice problems, correct? Or do you want to listen to a what, when, where show? Let me know. Okay, so someone to show. So yes, let's watch one round of the show. We have 6 minutes or some more, and then we will do more problems if you decide to stay. Let's see, moment. Что, где, когда. I hope you're excited, guys. I love that show. Here we go.
Господин Новиков, когда я впервые прочел этот вопрос, мое сознание перевернулось. Я даже предположить такого не мог. Внимание! Дрессировщик черепах.
Okay, so guys, so I have, before you continue, so Christina, I rarely guess the answers. I'm not that good, right? I guessed a few times, and one time they completely were wrong and I knew the answer. So very rarely. I mean, I might guess, I would say, at the very best, 5% of the time, and probably less, right? But I don't always watch it, right? So guys, here, are you ready? So it's very, very special type of skill, and you need to think fast and you need to work as a team. But some people are very, very good at it. Okay. So attention, guys. Here is the question. The trainer of turtles. Ready? You see this picture?
Перед вами картина турецкого художника Османа Хамдибея.
In front of you is a painting of a Turkish artist, Osman Khadibeyev.
Дрессировщик черепах.
A trainer of turtles.
Оказывается, в начале XVIII века при дворе султана
It appears that at the beginning of the 18th century, at the court of the Sultan,
черепах дрессировали.
turtles were trained.
Их приучали не стоять на месте, а все время передвигаться.
They were taught not to stand in one place, but move all the time.
Внимание, вопрос.
Attention.
Как
Question.
использовали черепах во время придворных вечеров на открытом воздухе?
Attention, the question. How were the turtles used during festive celebrations in open air? You understand? The turtles were trained to move about and not stand in one place in the 18th century by the Turks. The question is, how were they used at the Sultan open air parties? They were waiters. That's a good idea, right? So you see, that's how you play. They were waiters. So how were they waiters? More precise. You need to be very precise for this game. Served refreshments. And how would they sell refreshments? So they would kind of be like, that's a good idea, right? Walk around so that you could get something, but turtles are slow, right? So how long will it take you to get the refreshment? Any ideas? Other ideas? This one, by the way, I guessed. Spelled words. Went to college, those turtles, I guess, right? Always were late to exams. Swimming around in the pool to enjoy the people. They never served. Parades, like march parades or something, right, with the turtles, right? So other ideas. And once you're tired of waiting, they were painted with what? Ah, okay, convenient trash can. Interesting. Interesting. All right. Any other ideas? So here you go, guys. That's how you play it. And then, of course, let me show you how the game is running.